So today we're going to talk about, first of all, we're going to talk about computer output. All right, so this is 3.2E, by the way. Remember that you have a workout that's due tomorrow, and they are labeled next to the problems what section it's from. Any section where you see computer output is going to be labeled 3.2E. The good news is this is not that hard. It's just knowing what in the heck this all means, and that's what I'm here for, is to tell you. So let's read our example here. When Mentos are dropped into a newly opened bottle of Diet Coke, carbon dioxide is released from the Diet Coke very rapidly, causing the Diet Coke to be expelled from the bottle. Looks like a fountain, if you've not seen it. Will more Diet Coke be expelled when there is a larger number of Mentos dropped into the bottle? Well, two statistics students wanted to know. They use 16 ounce or 2 cups. Okay, 16 ounces is equivalent to 2 cups. Of bottles of Diet Coke. They dropped either 2, 3, 4, or 5 Mentos into randomly selected bottles, waited for the fizzing to die down, and measured the number of cups remaining in the bottle. Then they subtracted this measurement from the original amount of 16 ounces or 2 cups, and they calculated the amount of Diet Coke expelled in cups. Output from the regression analysis is shown below. On the left here, we have a scatter plot with the least squares regression line. On the right, what kind of graph is that? There it is. That's the residual plot. That's the residual plot, all right? It says the word residual on the y-axis, and it is the plot of the distance of the residuals. There it is. All right, and then down here, we have our computer output. Okay, so before I launch into computer output here, I want to write an equation for you guys. Y equals 2x plus 3. Looks like the equation of the line, doesn't it? It would, in fact, be an equation of a line. Y equals 2x plus 3. What does the 2 represent? The slope. What does the 3 represent? The y-intercept. Okay, I'm going to rewrite this equation. What does the 3 represent? The y-intercept. What does the 2 represent? The slope. Okay, perfect. All right, all good. All good things. Okay, so here is the next question. Which of these numbers is considered a constant? The 3 or the 2? The 3. The y-intercept is a constant. A constant is just a number that stands alone. It's by itself. It doesn't change. It has no variable attached to it. What number is considered a coefficient? The 2. It is the coefficient of the x. Are you guys all with me so far? All right. That was your 7th grade algebra linear review. So let's look at this table. Notice that in this table, it has the word constant. It also has the word coefficient. Okay? So the constant, what did you guys tell me the constant was in this problem? What did it represent? The y-intercept. The constant represents the y-intercept. So this number right here next to where it says constant, guess what that is? That is the y-intercept. That is our y-intercept. In fact, this entire line where it says the word constant is all about the y-intercept. That entire line is about the y-intercept. This particular number right here is the A value for our regression equation. Remember, our regression equation has this format of y hat equals a plus bx. So the a is our y-intercept, and we just found out what the a is by looking at our computer output. Pretty easy, right? The constant is the y-intercept, and it's the first number that you come across in the computer output. All right, if you guys look at the graph, the scatter plot, and look at the x variable, what is on the x-axis? What variable is on the x-axis? Mentos. Notice what it says right here underneath constant. It says Mentos. This entire line, the second line, is all about the x variable. Mentos is the x variable, and this whole line is about the x variable. This is where the coefficient part comes in from up top here. The coefficient of the x variable, what sits in front of the x variable? What does that B indicate? Slope. Guess what that number is? There's your slope right there. Easy. Right there. That is your b value. That is your slope right there. It's the coefficient of the x variable. It's the slope. So right there, those first two numbers are the most important two numbers in your computer output. You have your y-intercept, you have your slope, and now you can write the equation of the least squares regression line, which is what we're going to do. And this is part A on your paper, by the way. So part A, here we go. Let's write our equation. Expelled hat, that's the y value, amount expelled. Hat means we're predicting. So expelled hat equals 1.00208 plus 0.07083 times Mentos. There we go. That is the equation of the least squares regression line. I got those numbers right here from this computer output. Do you guys have any questions on that? Yes.
Are we gonna have to look at more graphs like that, or like tables?
Computer outputs, yes. But they're always the same, like meaning they're always in the same order, same position. The only thing that changes is the numbers. Yeah, but the position is always the same. So it's not like you're going to have to go hunting for where's the constant, where's the slope, whatever. It's always going to be constant, x variable, and this is always the y-intercept, this is always the slope. Yes, sir?
So if we put on the test y equals 1 point blah, 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 would that be wrong?
In the equation?
Yeah.
So if you put y hat equals, you can do that as long as you say somewhere else that y is the expelled amount. So if you write the word in the equation, you don't have to define the variable specifically. But if you use x and y, you do have to say what x is and what y is. Cool, yes?
What is
Expelled,
expelled?
so that's just a part of this problem. We're talking about the amount expelled in the Diet Coke example with the Mentos. So it's how much amount, or what amount of Diet Coke is expelled in dropping Mentos in it. Yeah, it's just the particular variable we're using. Anything else? Okay. The next thing here says SE coefficient. That stands for standard error of the coefficient, and you don't have to know anything about that until March. Yay! The next thing is the t-test statistic. You don't have to know anything about that until March. The next thing is, it says P, but it actually stands for p-value. You don't have to know anything about that until like April. Just getting better and better. I know, right? It's so good. All right, so down here, these should look familiar. What is S? What does S stand for? We learned that last Thursday. Standard deviation of residuals. This is our standard deviation of the residuals. Here's what it means. This is how far from the line our predictions will typically vary. Now, the standard deviation of residuals is in terms of whatever units the y variable is using. Our y variable here was using cups. So this is how many cups our predictions will typically vary by. Okay, this is how many cups our predictions will typically vary by. All right, r squared. You guys know r squared? Talked about that last week as well. R squared, this is r squared. It's 60.2%. That is 60.2% of the variation in my y values can be explained by this particular linear model. That means 60.2% of my data is going to be within one standard deviation of the line. Is that a good line? Not terrible. I mean, 60% of my predictions are going to be good. That's not terrible, okay? Last one here is r squared adjusted. This you will never use in your whole life, ever. Don't do it. It's dumb. What that does is it kind of adjusts out some of the data that is a little bit, influential or outlier-ish. And we don't want to adjust that stuff out. We want to make sure we include all the data in our analysis. So you guys will actually never use that value. Got it? That's how you read computer output. Do you guys have any questions on reading computer output? Well, all right then. Let's just do a few examples to refresh our memory from some other things we've done. So the first thing we already did, part A. Part B, what is the correlation? What notation do we use for correlation? Correlation. It's a letter. R. The notation for correlation is R. Did we get told anywhere what R was?
R squared.
We were told what R squared was. And if we know R squared, is there any way to get R?
Actually.
That was the funniest joke I've heard. Yeah. How do I get R from R squared? I'm going to take the square root of R squared. So I'm going to take the square root of 0.602. The square root of 0.602. What is the square root of 0.602? $776, anyone?
Yes.
All right. Let's interpret this. What does that mean? R is correlation. It tells you two things, strength and direction. How strong is this association? Strong. Positive or negative?
Positive.
How did you know it was positive?
And that one is both.
Ah, see, that's where we're a little bit wrong.
We need to look at R squared.
Here's the deal. Remember, if I take the square root of R squared, I could get a positive or a negative. Because remember, the square root of 4, positive or negative 2. Remember that? What's the square root of 4? It's either positive or negative 2. Oh, yes. Okay. So how do I know that this is positive?
The graph.
Look at the graph, you guys. The graph has a positive trend. This is, in fact, positive, okay? So just to remember, you got to make sure you check that graph to see what the R sign is. All right, so here's what we know. We know that there is a strong positive correlation between amount of coke expelled and number of Mentos used. We have a strong positive correlation between amount expelled and number of Mentos used. Cool? Cool. All right, what is the coefficient of determination? This is a very fancy way to ask you guys, what is R squared? Now that was given directly to you. What was R squared? $60.2. All right, so we're going to interpret R squared now. 60.2% of the variation in amount expelled can be explained by the linear model relating amount expelled to number of Mentos used. So in this particular unit, Unit 3, there's a lot of sentences, a lot of interpretations. That was on that sheet that I gave you guys last week that had all the different interpretation sentences on it. There's really, out of those, there's about 2 or 3 that are, pretty specific. I would say slope is fairly specific, making sure you're always saying for every increase of 1 in the x, there's a change in the y or whatever. But this one, if you're only going to remember one sentence from this unit, let it be this one, the R squared sentence. It is the percent of the variation in the y variable that can be explained by the linear model relating the y to the x. That is the most important sentence in this entire unit, and maybe even the most important sentence to recognize for the year. So this sentence is extremely important to know. This sentence will show up in funky ways. You will be asked on things like your test to identify what percent of the variation in the y variable can be explained by the linear model. And you'll basically just have to write down what R squared is. But it sounds real fancy, right? All we're asking is what's R squared. It's just a fancy way to ask it. So make sure you guys can recognize this sentence and you can write this sentence and you know this sentence. This is the most important one of the week, of the year, of your life. Okay. Is the linear model appropriate? How do you tell if the linear model is appropriate?
No megaphone, no curve.
No megaphone, no curve in what?
The graph.
What graph?
The non-residual.
The residual plot. That's the one that's on the right side of your paper, guys. Look at that one, the residual plot. Do you see a curve pattern?
No.
Do you see a megaphone?
No.
Is the linear model appropriate?
Yes.
Beautiful. When you answer this question, make sure you reference the residual plot. Yes, the residual plot shows no curved or megaphone pattern. The residual plot shows no curved or megaphone pattern. Questions about any of that? Yes, ma'am?
What makes the curve or megaphone pattern inappropriate?
So if I have a curved pattern in my residual plot, so let's say I see this, that means my original line is doing something, I'm trying to fit a line to data that looks like that, and that is very clearly not linear. Sometimes the data, it's a little harder to see it when it's it has a slight bend in it. And so like when you have the line, it kind of masks the curve. So when we put it on a residual plot, we look at the distance from the line to the data values. If they're all super close to the line, it helps magnify that curve so we can see that the linear model was not a good fit. Yeah. All right. Let's look at a couple more questions here. First one says, would you be willing to use the linear model to predict the amount of Diet Coke expelled when 10 Mentos were used?
No.
Why not, Dylan?
I don't want to.
You just don't want to?
Because
Just because.
Because you already divided R by 2. I'm so sorry.
Because it's off the X value.
I am really so sorry.
You guys, what were the X values on our graph, on our scatter plot?
1 point something.
5.
2 to 5. We only tested with 2 to 5 Mentos. 10 would be double what we tested with. That would be an extrapolation. Everybody say extrapolation. So this should be a no. This would be, or that would be an extrapolation. And that would be a problem. I would bet $2 that if we did plug in a 10, that we would expel more Diet Coke than we started with.
I would agree with that.
I bet that would happen. Jack's going to check for us. Because we're going to expel more than 2 cups. Bet.
Oh, with 10 Mentos, yeah. I would hope so.
But how are we going to expel more than we started with? We can't. Why? This is a bad idea.
Or
Yes.
It's a wonderful idea and we're creating more.
We might.
We are
creating
breaking
matter.
We are. We are math magicians.
I'm a method.
You know the Diet Coke's going up and then back into Canada and up.
This is a Coke ad.
What do you think, Jack?
Nope.
We would not be expelling more?
It would be 1.7.
1.7. Oh, wow. Snap. We could have done it.
Have you been
Wow.
telling all of your classes
I sure
that
did.
it's extrapolation?
Wow. Well, it is still extrapolation.
Okay. Well,
It is still extrapolation, but
You scammed them.
I did scam
Yeah.
them. Dang it. I hate when that
You
happens.
cheated them out of like more information that they could have had.
Tear. All right. Well, you know what? They'll survive. So let's look at this.
Within the R value, you could potentially have more
Oh.
expel than 2. So
Oh. That's not good.
it's,
Yikes. Okay. That would be bad. So yeah, we won't. Let's not extrapolate. All right, you guys. If the amount expelled, that's our y-axis. If it was measured in ounces instead of cups, how would it affect r squared?
It wouldn't.
You're absolutely right, darling. R squared is not affected by unit changes. R squared is not affected by unit changes. R is not affected by unit changes, so R squared is not affected by unit changes. R and R squared are hardy people. But what about S? S is the standard deviation of the residuals. It tells us how far the data is from the line, and it is in terms of the Y units. So if I change the units from cups to ounces, will it change my S value? It will. It will. And here's why. If I change my Y units, which that's what units my S value is changing, it will change by whatever the conversion factor is. Do you guys know how many ounces are in a cup? 8. 8 ounces in a cup. There are 16 ounces in 2 cups, according to the problem.
I didn't read the problem.
Oh, okay. There are 8 ounces in a cup. So if I change from cups to ounces, I just need to multiply S by 8, and that will get my S from cups to ounces. That's all. So S has the units of the Y variable and changes by the same conversion factor. So for that one, if I needed to get it, I would just multiply by 8. I would multiply S by 8, and I would get how many ounces that would be. All right. What questions do you guys have about computer output or any of this other stuff that we've reviewed? 0 questions? Awesome. So we're going to now shift gears into 3.2F. This is our last little section, and it is basically a calculator problem. Yay! Also some algebra. Yay! So in order to warm up our brains, I'm going to give you guys a little algebra warm-up. Are you ready? Let's do it. Here's an algebra warm-up for you. I have given you 5 variables that have been defined with numbers. I've given you 2 equations. This equation on the left is B equals R times D over C. This equation on the right is G equals A plus BF. I have given you C, D, G, F, and R, and I want you to solve for A and B. Are you ready? Go. Okay, if I just plug in what was given to me, there we go, then I would get B equals 0.75 times 12.6 over 5.4. And that I could just plug in my calculator and get the answer to. So what does B equal?
1.75.
Cool. All right, and then over here I've got 143.1 equals A plus B, and then F was 123.5. So that's what I would get if I plug that in. Obviously we have a problem here. We have two unknowns, A and B, but B is no longer unknown. B is right there. B is 1.75. So if I plug in 1.75, then I can use amazing algebra to solve this problem. What was the 1.75 times 123.5?
216.125.
So then I would subtract that from both sides. And I would get that A equals negative.
73.025.
Perfect. I have A and I have B and nobody died from it. Yay. Why in the world did I do this with you?
To make sure that we get it all straight.
Yeah.
I get the first part.
Yep. To make sure that we have our algebra skills ready, because now we're going to do this, but in context of statistics. Okay? So, it's the same thing, you guys, but the formula looks slightly different. Okay? And here's why. There's two formulas. They are both on your AP Statistics formula chart. Okay? They are right here. The first one on the top says y bar equals a plus b x bar. That looks very similar to the g equals a plus b f formula we just looked at. So y bar equals a plus b x bar. B equals r times s sub y over s sub x. Those two formulas are going to be given to you on every test from here for the rest of your life with statistics. And you can use those formulas. This is how you're going to write the equation of a least squares regression line from what's called summary statistics. You're going to use those formulas, okay? So let's do that. I will rewrite the formulas here so we can kind of write down what they mean. So here they are again. The first one was y bar equals a plus b x bar. What does y bar stand for anyway?
Average.
The mean of the y's. That's the mean of the y's. A, we know what A is, right? What is A in our equation here? That's our y-intercept. B, that's our slope. Okay, x bar. What's x bar? That's the mean of the x's. That's the mean of the x's. All right, so we have the mean of the y's, the mean of the x's. Those would be given to you somewhere in the problem. Then we have this other formula. B equals r times s sub y over s sub x. Obviously, B is the slope. It's that same B that's in the slope formula. What does R stand for? That's correlation. That would also have to be given to you in the problem. S sub y. What does S sub y stand for?
Sum of the y's.
Not the sum of the y's.
Standard deviation.
This is the standard deviation of the y's. This is the standard deviation of the y's. This would be given to you in the problem. S sub x. What do you think that stands for? Standard deviation of the x's. You got it. Cool. So now we know what everything means. These values would be given to you, these 5 things. Mean of the y's, mean of the x's, R, correlation, standard deviation of the x's, standard deviation of the y's. All those things would be given to you in the problem. you would use these formulas to just solve for A and B, and then you would be able to write your least squares regression equation. Y hat equals A plus BX. So you would have solved for A and B, and then you can write the words for the Y and the X variables. Okay? Ready to do it? So exciting. Yes. Huh?
Shipper me.
It's only Miss Lake, it's only giving one question on the test.
I will just be completely, fully, 100% honest with you. This is a free response question. So you're going to have to do this on your own, by yourself, on the test. Here's the great news. The homework that you have that's due tomorrow, there's 2 of these on the homework for you to practice with. There's also one on the review. So you will do it at least 3 times between now and the day of the test. In addition to this right here. Here we go. Hayden's loving his life right now. In Miss Lakey's AP Statistics course, the correlation between the students' total scores prior to the final examination and their final exam scores is R equals 0.6. R equals 0.6. There's the correlation. The summary statistics of pre-exam and final exam scores are in the table below. Miss Lakey has lost Adam's final exam, but she knows that his total before the exam was 300. He had 300 points before the exam. So she decides she's going to predict his final exam score from his pre-exam total. Seems reasonable. Here's some data. The pre-exam mean was 280. The pre-exam standard deviation was 30. The final exam mean is 75. The final exam standard deviation is 8. And now we just need to find the equation of the least squares regression line. Sounds fun, right? Here we go. First task. Which one is X and which one is Y? Which one is the X variable? Pre-exam or final exam? Yeah, pre-exam is the X variable. Final exam is the Y variable. Here's what this means, you guys. 280 is the X bar. It's the mean of the X's. 75 is Y bar. It's the mean of the Y's. Standard deviation of the pre-exam is S sub X. Standard deviation of the final exam is S sub Y. We have all 5 things we need to use those formulas. B equals R times S sub Y over S sub X. R was 0.6. Now, I'm going to tell you guys that the most common mistake is right here. People will take this 30 over 8 and put it right here as 30 over 8. Why would that be wrong? This should be Y over X, very much like your slope is Y over X. Rise over run. So slope, this is what we're finding here is slope. So you need to have Y over X here. So you got to make sure you don't get caught in the trap of putting it the way it is in the table. 0.6 times 8 over 30 is 0.16. There's my B. There's my B. There's my slope. Now I can use my other formula. Y bar equals A plus B X bar. Y bar equals A plus B X bar. 75 equals A plus 0.16 times 280. All I did was plug in what I knew. Now we're going to do some algebra. What is 0.16 times 280? All right, now to get that A by itself, I'm going to subtract 44.2 from both sides. I have A, I have B, I'm ready to write an equation. Final hat. because that's what I'm predicting. Final exam, predicting, hat. There you go. Final hat equals 30.8, that's my A, plus 0.16, that's my B, times pre-exam. That's my variable for X. That is the equation of the least squares regression line from summary statistics.
That's not bad.
It's not bad at all. That's not bad at all. That's actually kind of fun.
That's so much fun.
It is the
This
funnest.
is my free time.
I know, right? Me too. So now, guys, we're going to use this equation and actually tell Adam what he's going to get on his final exam since I lost his test. So, Mr. Adam, here we go. Final hat equals 30.2 plus 0.16 times, what am I going to plug in?
Oh, it's 30.8.
30.8, thank you, times 300. Because little Mr. Adam had 300 points going into the final exam. So, this you just plug it in your calculator. 30.8 plus 0.16 and 300.
$78.8.
78.8? Well, Adam,
That's not too good.
is he happy?
I would be mad at my teacher.
Well, look at this. Adam doesn't think that this method accurately predicts how well he did on the final exam. Adam says, Miss Lakey, you lost my exam. I studied hard for it. This is not a representation of me. How's he going to prove me wrong? Well,
Take it again.
I'm going to say, here, Adam, take it again. He's going to say, I took it already. It's not my fault. You lost it.
200. That's fair. On my 100.
So Adam is going to tell me, Miss Lakey, the R value was only 0.6. That's just moderate. And R squared is the percent of the predictions that are good. So, what is 0.6 squared? What's 6 squared, you guys?
36.
Okay.
Oh, that is how that works.
So only 36% of your predictions with this line, Miss Lakey, are any good.
Okay. He definitely did good. He's like saying all this stuff.
If he knows all this, I'm going to give him a higher grade.
Yeah.
I'm going to go ahead and give him that 95. I can't give him 100, but I can give him 95. Let's go, Adam. All right, so 36% of the variation, this is that sentence again, 36% of the variation in final exam score can be explained as soon as I can spell explained by this linear model. Translation, this prediction stinks. Adam should get the chance to prove, which I think he has at this point, that he knows what he's doing. Cool?